Hello everybody, my name is Wade Gabriel, Associate Professor of Clinical Medicine at Methodist University. Today we're going to discuss Part 1 of acid-base disorders. This includes general concept and compensation. Part 2 will include anion gap and delta ratio. Suppose that you are working in a factory and the fumes that are coming from the burners are clean, as you see on the left side, and all of a sudden you found the fumes not clean as you see on the right side. What are you going to think in? There are three possibilities. The type of fuel has been changed, or no enough oxygen to burn the fuel completely, or the chimney is not clean. Same thing in our body. If we burn carbohydrates with enough oxygen, we'll get clean energy, that's to say, resulting in CO2, which dissolves in water and gives carbonic acid. We get rid of carbonic acid at the lung as CO2 and water, or at the kidney as hydrogen excretion and reabsorption of bicarbonate. And this way, as you see, the acid produced from burning carbohydrates is mild. We call it volatile acid, and very easily get rid of at the lung CO2 and at the kidney hydrogen. But we don't only burn carbohydrates. Sometimes we break down proteins or lipids. If we break down proteins, we're going to produce sulfuric acid. If we don't have enough oxygen, we're going to produce lactate. If we don't have insulin, we're going to produce keto acids. These acids are strong acids and we to buffer them. We'll take sulfuric acid as an example. Sulfuric acid will react with bicarbonate and result into carbonic acid and sulfate. This way we get mild acid, carbonic acid, the body can get rid of very easily. At the lung or the kidney, you have to note that the difference between volatile acids and non-volatile acids or pathological acids is the formation of anions like sulfate, lactate, phosphate. Suppose you have a patient with acidosis. We have to answer these questions. Is the problem in the process of production of energy, or the problem at the lung, or the problem at the kidney? If the problem at the lung, we call it respiratory acidosis. If the problem at the production of energy or at the kidney, we call it metabolic acidosis. We have three important questions that need to be answered, and I'm not going to give you the answers now. We're going to conclude the answers. The first question: is acidosis due to retention of carbon dioxide or loss of bicarbonate? The second question: is there more than one problem? Maybe both of them, retention of carbon dioxide and loss of bicarbonate, and we have abnormal fuel. So we have to decide, is it one cause of acidosis or more than one cause? Another question: is the cause bicarbonate lost at the kidney or consumed with pathological or abnormal acids. In other way, is the kidney at fault or the production of energy is faulty? There are two factors which are going to set the pH: CO2 and bicarbonate. Henderson-Hasselbalch equation governs the relation between pH, bicarbonate, and CO2. If we disregard the constants in this equation, we're going to find out that pH is proportional to concentration of bicarbonate over or divided by PaCO2. So, increase in bicarbonate will result in increase in pH or increase in alkalinity. Increase in CO2 will result in decrease in pH. In order to have pH balanced, we have to have a balance between bicarbonate and CO2. This balance is achieved by compensation. So if we increase CO2, we increase bicarbonate to get the same pH. If we decrease bicarbonate, we decrease CO2 to get the balance to the same pH. This is a very important concept. And please do not put CO2 as numerator. And remember that when pH increases, alkalinity is higher. Now we'll try to answer the first question. We have a patient with acidosis. Is acidosis due to retention of CO2 or loss of bicarbonate? In this table, the red arrow will indicate the primary change, and the blue arrow will indicate the compensation. If the primary change is retention of CO2, as in the third row, this will result in respiratory acidosis, and in this case, the pH will be less. So increase CO2, decrease in pH. The arrows are in different directions. The blue arrow will indicate compensation. If the primary problem is loss of bicarbonate, this will be metabolic acidosis, as in line 1. And you note that the pH will decrease. Please keep in mind that pH is proportional to fraction. Its denominator is CO2 and its numerator is bicarbonate. Now we can answer the first question. Is the problem respiratory, or in other words, retention of CO2, or metabolic, loss of bicarbonate, and vice versa for alkalosis? The answer is, look at the directions of the arrows. If PaCO2 is drained in the same direction as the pH, the acid-base disorder is metabolic. If PaCO2 is drained in different direction to pH, the disorder is respiratory. Now we need to answer the second question. Is there more than one problem? Because there may be more than one problem, and the change in pH is the net result of both problems. In order to answer this question, we have to understand compensation and decide if compensation is adequate or not. To identify the presence of a second acid-base disorder, we have to look into compensation. If a given patient is not compensating as predicted, a second or maybe a third acid-base abnormality must be present. What do we mean by as predicted? We mean as should happen or should occur in a normal individual with only one problem. With only one problem. For example, if in a normal individual with respiratory acidosis, CO2 increased, what his bicarbonate level will be to compensate for the increase in CO2. This is the predicted normal response in an individual with normal other factors, lung, kidney, with one acid-base disorder only. Then we compare this normal response, or what we call predicted response, to the response of the patient and to compare them. If the patient has the same response, this means he is compensating well. If the patient has a different response, this means that his compensation is not adequate, or he may have another acid-base problem going on, and what we see is the sum of both processes. What are the rules of compensation? The body attempts to compensate for acid-base disorders in such a way to mitigate derangements of arterial pH, but never overcompensate or even return to normal. If you have a shock absorber, as you see on the right side of the picture, then you put a rock on this shock absorber, as you see on the left side of the picture. It is logic that with the rock over the shock absorber, the shock absorber will be compressed and will never return to normal until we release the weight of the rock. Same thing in the human body. The rock represents, for example, a process of acidosis is going on. The pH will not return to normal until we stop this process of acidosis. And it is logic that we never overcompensate. To summarize the rules of compensation, measured value should be near predicted value, and now we understand what do we mean by predicted value, and we're going to explain how to calculate the predicted value. Rule number 2, primary metabolic disorder will result in respiratory compensation, and primary respiratory disorder will result in metabolic compensation. And as you remember, pH is proportional to fraction bicarbonate over CO2, and in order to keep this fraction constant, if we increase bicarbonate, we have to compensate by increasing CO2 and vice versa. This scale represents the balance between CO2 and bicarbonate. If the scale is balanced, pH is around 7.4. If the scale tips to the right, this means there is alkalosis. If the scale tips to the left, this means there is a process of acidosis. So alkalosis can be produced by increase of bicarbonate or by loss of CO2. Acidosis can be produced by increase of CO2 or loss of bicarbonate. And to achieve compensation in case of loss of bicarbonate, we have to lose CO2 also, and vice versa. Remember, I mean by balance, not equal amounts, but just balance. If there is a process of metabolic alkalosis, the scale will tip to the right, and compensation will be by retaining more carbon dioxide. This slide represents a normal or predicted respiratory compensation, and as you see, the scale never returns to normal balance as long as the metabolic alkalosis is going on. What about if we find the scale is balanced to the normal balance position? Then we should expect there is another process of respiratory acidosis that is going on in addition to the predicted respiratory compensation. Now, we need to know how to calculate the predicted patterns of compensation and compare these calculations with the actual compensation of the patient. To calculate compensation or predicted compensation in metabolic acidosis, we look at the last two digits of the pH and the value of pCO2. There should be the same or near each other. So if pH is 7.32, pCO2 should be 32. Or we can apply Winter's formula. Expected PaCO2 equals 1.5 serum bicarbonate plus 8 minus or plus 2. Or we use this rule, which is the easiest. For 10 units decrease in bicarbonate, there will be decrease 12 units in CO2. For compensation in metabolic alkalosis, for each 10 units increase in bicarbonate, there will be an increase of 12 units in CO2 as a compensation. How fast does compensation occur? Metabolic compensation for a primary respiratory disorder takes 1 to 5 days to be completed. We need time to build up or get rid of bicarbonate by the kidney. However, for respiratory compensation, the process is much faster. We start quickly, but it takes about 12 to 24 hours to be completed. So, for primary respiratory process, we have acute and chronic, in addition to acidosis and alkalosis. So we have 4 possibilities. To make it easier for you to remember the rules of compensation, I put all of them in one table. What you need to know from the history, is it acute or chronic respiratory process? And this is from the history in the vignette. If it is acute respiratory acidosis, we need to calculate the bicarbonate. Remember, in all respiratory processes, we calculate the bicarbonate as a compensation and never ever do the opposite. Don't get confused. Calculate bicarbonate for respiratory processes. Calculate CO2 for metabolic processes. So if we have acute respiratory acidosis, we calculate the bicarbonate. For each 10 units increase in CO2, there should be an increase of 1 unit of bicarbonate. So the ratio here is 1 to 10. And note that I put a question mark for the value that you need to calculate through this table. This table makes everything easy for respiration. The ratio is 1 to 10, 2 to 10, 3 to 10, and 4 to 10. You just remember 1, 2, 3, 4 to 10 in this order. Acute respiratory acidosis and alkalosis, then chronic respiratory acidosis and alkalosis. And that's it. You don't need to remember anything else. I added in the same table the rule for metabolic acidosis and alkalosis, and here remember I put the question mark next to the CO2. We need to calculate CO2 and not the bicarbonate. And to make the ratio easier for you to remember, I make it 10 to 12 for metabolic acidosis and 10 to 7 in metabolic alkalosis. Remember that we calculate the predicted value, and these ratios are calculated as change and not absolute, and this is change from the normal, considering bicarbonate 24 and CO2 40. This table shows what we need to calculate as predicted value, and we compare what we calculate with the value in the patient. So for respiratory processes, we calculate bicarbonate. For metabolic processes, we calculate CO2, predicted value. Now let us practice some cases about compensation. Evaluate compensation for the arterial blood gases. Please pause the video and try to answer if compensation is adequate or not. First step, check pH. There is alkalemia, and please note that there is a difference between alkalemia and alkalosis. Alkalosis is a process that can lead to alkalemia. When the pH is above 7.44, It is alkalemia. So, can we have alkalosis and acidosis? Yes, we can. Can we have alkalemia and acidemia in the same patient? No, we cannot. So, then we check the PCO2. There is increase in PaCO2 and increase in pH. So the increase in the same direction. This is metabolic alkalosis. Then we check for compensation or evaluate compensation. This is metabolic alkalosis. The compensation should be 10 to 7. 10 bicarbonate, 7 CO2. Change from normal. The patient bicarbonate changed from normal by 12. This is from 24 to 36. So his predicted change in CO2 is 8.4. So CO2 should be 8.4 plus 40 equals 48.4. This number is close enough to the actual PaCO2, so compensation is adequate. Case 2. Please pause the video and try to evaluate compensation for the given arterial blood gases. We check pH, there is acidemia, and for sure there is acidosis. One process at least of acidosis. There may be other processes. The change in CO2 and pH is in the same direction. So we have metabolic acidosis. To evaluate compensation for metabolic acidosis, we have 3 ways. Here we are going to apply Winter's formula. Predicted CO2 equals 1.5 times the bicarbonate plus 8. So 1.5 of 10 is 15 plus 8 equals 23. But the patient's CO2 is 32. So the actual CO2 is higher than predicted. High CO2 means there is respiratory acidosis in addition to metabolic acidosis. Last example, a patient was found unresponsive on the floor. His arterial blood gases are pH 7.33, PaCO2 67, bicarbonate 35. Please evaluate compensation. You can pause the video and try to answer first. We check pH, there is acidemia, and for sure one process of acidosis at least. Check PCO2, the change of PCO2 is in opposite direction to the change in pH. So this is respiratory. And from the history, we can say it is acute. When we evaluate compensation from the table, we're going to look for the compensation in case of acute respiratory acidosis, which is 1 to 10 bicarbonate to CO2. So the bicarbonate should equal, or the change in bicarbonate should equal 2.7. The normal is 24. So the bicarbonate of the patient should be 24 plus 2.7, which is 26.7. Bicarbonate here is 35, so it is higher than predicted, and the patient has metabolic alkalosis in addition to respiratory acidosis.